So chapter number 4, the periodic table. The periodic table is actually divided into many parts, but the simplest kind of classifications, and this chapter mostly consists of classifications. Classifications are actually the ways we can classify the periodic table. We can classify the periodic table by many ways. First, we're going to discuss the most common way we have discussed before, a little touch of it actually, groups and periods, right? I'll just explain as soon as I move ahead what groups and periods are. The second way to classify is to talk about the differences between the elements, and we generally categorize them into metals, non-metals, and even metalloids. We'll discuss that too. Moving forward, the third way is to classify them according to their electronic configuration. We'll discuss that too. And we'll let you know how electronic configuration is related to groups and periods. And then lastly, important groups or important periods, we also call them important families. Different books, different names means the same thing. We're going to actually point out a few important parts of the periodic table, important in terms of because of the abundance of elements around the planet, or important because of your syllabus content as well. All right. So that's what we will be doing in this entire chapter. To begin with, I'm going to just clear it up, and we're going to discuss the simplest or the first on the list, that was groups. The vertical columns are actually known as groups. So there is 1, there is 2, there is 3, 4, 5, 6, 7. We call it sometimes 0, sometimes 8. 0, however, is a better explanation to it. You would notice that we haven't categorized this whole part. We haven't categorized these two long lines at the bottom. So yeah, they are also categorized into group numbers, but we don't teach those numbers at this level. To keep it easy, to keep it simple, we just divide the other ones, the ones on the left and the ones on the right, into group numbers. However, as soon as you move on to A levels, you'll see that these are also categorized into separate group numbers. The other term that we commonly use are periods. The horizontal rows are known as periods. They are numbered as 1, 2, 3, all the way to 7. So we have 7 periods. Although these are groups are numbered in the same way as periods, but some of the time you would notice that these groups are also written in Roman numbering, which is we use capital I's and V's to represent them. So that's how we write group 1, 2, 3, 4, 5, and so on, all the way to 8. However, we're also going to call it 0. Why? I'll discuss all the little details as soon as we move on. One thing we need to notice over here is that the elements are arranged in the order of increasing proton number or increasing atomic number. Proton number and atomic number were the same thing. So it means that we're going to go with the horizontal lines with increasing numbers. So if this is 1, this is 2, this is 3, this is 4, as I have already explained that this is the identification number, kind of an identification number for the elements. So it's easier to put them in this order. So it would move on from left to right, all the way from top to the bottom of the table. However, there are 2 stops in between. You'll notice a single dot over here, and you'll see an entire line made out of this single dot. Actually, the elements were supposed to be inside the periodic table, but if we put them inside, they actually interrupt the entire table. As you can see, there are a lot of elements that we were supposed to put, and everything in the periodic table will not show its properties in the same way as they were supposed to if we put them inside. So what we did is that we put a symbol over here and a long list of elements along with the symbol. And then in period number 7, you're going to see a different symbol, a double dot, and you see the same list of elements. I mean, the same number in terms of the list, but the elements are, of course, different. And we see that symbol at the bottom. So we have actually 2 rows in which there are elements, and which, if were put in the periodic table would get interrupted. So we have put them separately. One of them are known as lanthanides, one of them are known as actinides. This is as far as we need to know about these, as these are the ones which consist of most of the elements that humans are not completely aware of. Some of them are elements that we still call a mystery for humans. They are so rare that we don't even have the amounts to perform experiments on them, get to know them a little better. So that's why we don't teach these at this level. So if you ask me, what we are mostly concerned with are the two groups present over here. So mostly the purple elements and the green ones over here, and a little bit of orange ones on top. That's about it, what we are going to go with in your entire O-level, this IGCSE course, all right? So this explains the groups and periods classification. Now, if you take a look, you would notice that the bonds in the center are named as transition metals. There are some non-metals over here, which we are further going to bifurcate. I am talking about the ones in green. The ones in purple are actually reactive metals. Hydrogen is the only one which is in blue. Later on, we are going to call it a unique element. We'll explain why we call it a unique element and what properties actually make it unique. Sometimes you won't see this hydrogen over here. Sometimes you will see this hydrogen on top separately from any group, but of course in the same period as helium. H is hydrogen, He is helium. That's about it for the starting introduction of periodic table. Let's move ahead. We'll come with more detail as soon as we move further. So the vertical columns are groups 1 to 7, final group is 0. The elements in orange are transition metals. They have numbering, but we don't consider them here. Some groups have names. These are the important ones which we need to discuss. Group 1 is alkali metals, group 7 is halogens, group 0 is noble gases. These are the ones you need to know and memorize. We're going to discuss them in a lot more detail than the rest of the periodic table. Now, the horizontal rows in periodic table are called periods. So the first period is just hydrogen and helium. You'd notice that if we talk about periods, period number 1 has 2 elements, right? Period number 2 and 3 have actually 8 elements each. Period number 4 and 5 have 32 elements each, so on and so forth. Period number 6 has more elements than this, but the list continues. All right, sorry, this is not 32, this is 18, this one's 32, 7 is still incomplete. These are the number of elements just for the introduction. You might not need to memorize them. All right, this is giving you an idea that the top of the periodic table is mostly empty space, while the bottom of the periodic table is literally filled with elements, and most of the elements are actually present at the bottom. Lanthanides and actinides are actually dropped out of their original proper places, written separately at the periodic table. We have a good reason for this, but we'll do that later. If you go with this did you know part, you would see that group 0 is labeled as sometimes group 8. Sometimes the periodic tables are numbered from 1 to 18, including the transition elements, but that is kept for a later part. All right. Moving on, the periodic table in the number of protons, electrons, and neutrons. This is the part, this whole is the part which I said that we call as the classification of electronic configuration. Now, the periodic table and the number of electrons, protons, or neutrons an element has are very much related to one another. Remember 3 simple points, and it would be pretty easy for you to work with it. The number of protons in an atom is equal to atomic number. Number of electrons in an atom is equal to number of protons. We have discussed both pieces of details earlier. And the number of neutrons is simply mass number, which is denoted with A, minus atomic number, which is usually denoted by Z. So it's pretty simple. But how is this related to electronic configuration? Let's clear it out further, moving to the next portion. The arrangement of electrons in an atom is something that we need to properly understand and is also a part of the course. These are one of the most important and common questions from this chapter in specific. The electrons move around the nucleus in series of levels. We may call them shells, we may call them energy levels. The previous name were orbit, when the scientists were pretty impressed with the solar system model. They thought that the nucleus is present in the center of the atom, and all the electrons revolve around the nucleus, just like the planets revolve around the sun in the solar system. So they used to call these ones as orbits, but orbit is not a good word for them. We don't use it anymore, it's obsolete. We either use the word shell, or the term energy level is the best one to describe it. Now, in order to understand that, from the nucleus, the one that is closest is first level. This is known as first shell 2. The second one is second level, third level, so on and so forth, which makes actually numbering of levels pretty easy, as well as the naming. Now, each energy level or shell can hold a certain number of electrons. Lower energy levels are always filled before the higher ones. Not completely, but yeah, filled before the higher ones. This is a very important point you need to remember. The lowest energy level is the closest one to the nucleus. It only has room for 2 electrons. The second one has only room for 8 electrons. For the first 20 elements, the third level can hold a maximum of 8 electrons. What does this mean? This means that actually it can hold a maximum of 18 electrons, but I'm going to bifurcate it by explaining that it becomes stable at 8 electrons. What do I mean by the word stable? When I use the word stable, it means that this level is now filled enough that you can start filling the next level before you can completely fill up level 3. This means as soon as level 3 has 8 electrons, start filling level 4, and you can complete filling the level of third level afterwards. All right. This rule actually stands for almost every shell after the first shell. For second shell and subsequent shells, subsequent means every shell after that, it can be second, it can be third, it can be fourth, it can be fifth, sixth, seventh, whatever shell is that. It may contain a different maximum number of electrons, but it would have a different stability number. Stability number is the number of electrons by which it becomes stable enough for you to fill it up differently. For example, third shell can contain a maximum of 18 electrons, but become stable at 8, which means after putting 8 electrons, don't put any more. Start filling the fourth shell. And if we talk about the fourth shell, it can contain a maximum of 32 electrons, but as soon as it has 8 electrons, you can start filling the next one. So actually, stable number or stability number is the number of electrons by which a shell is stable, and you can start filling the next shell without completely filling the previous one. This is also explained over here. The third shell can actually hold up to 18 electrons. To explain why 2 electrons go into the fourth shell before the third shell is completely filled requires a more advanced understanding of electronic configuration. To give you a very brief idea, actually every shell is made up of a series of subshells, its bifurcations. Some of these subshells overlap from one shell to another. They have different names. The subshells are S, P, D, F. We name them differently. So the fourth S subshell, this one, in case of fourth shell, can hold 2 electrons, is lower in energy than the 3D one. So we can start filling the fourth shell even before we completely fill the third shell. That's why this happens. However, this is usually not asked in exams, so you only need to know the understanding about how to fill them instead of the whole reason, which is actually a kind of advanced understanding. Make sense?
Yeah.
Okay, let's move on then. This might come difficult to you, but as soon as we are going to practice it with some examples, it's going to come easy to you. Now, how to work out the arrangement of electrons in an atom? The arrangement of electrons, first of all, is known as electronic configuration, as I said earlier. Now, for chlorine, as an example, the atomic number is 17. So it has 17 protons and it has 17 electrons. Sorry, my bad. It was supposed to be 17. So it has 17 electrons that we can put. As we know, the first shell can only contain a maximum of 2 electrons. The second can only contain a maximum of 8. So if we put these electrons in the order, we are already done with 10 electrons. How many are we left with? 7. So in the third shell, obviously there are 7 electrons. It doesn't even become stable with it. So electronic configuration would be something like this, and here the total is 17. How are we supposed to write it? It's written as simple as that. The electrons in first shell, comma, the electrons in the second shell, comma, the electrons in the third shell. You can even replace these commas with dots, but commas are considered better in terms of electronic configuration. So these numbers are the electronic configuration numbers. Let's bifurcate these numbers a little more by, instead, let's not bifurcate it right now. You might find it difficult. Let's go with the drawing of electronic configuration, which is actually also the next topic over here in the book. We'll bifurcate it a little later. Okay, so how do we draw the electronic configuration? Remember, drawing or writing the electronic configuration are two different questions. If they ask you to draw an electronic configuration, you need to draw something like this. If they ask you to write the electronic configuration, you're supposed to come up with numbers like this. So make sure that you read the question carefully and work it out accordingly. All right. For example, hydrogen has proton number 1, so it only has 1 electron in the first shell. Helium has 2, which fills the first shell for it. The next one on the list is lithium. It has 3, so of course we're going to put 2 electrons in the first shell and the third one in the second shell. So on and so forth, you would see the entire second period filled over here. Beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Neon has actually a proton number of 10. So there are 2 electrons in the first shell and 8 electrons in the second shell. All right. So apart from that, some key points: drawing circles like this does not imply that the electrons are orbiting in the nucleus along the circles. The circle only represents the energy level. The further away the level is from the nucleus, the higher its energy is. So it's impossible to work out exactly how an electron is moving in energy levels. So don't just imagine that if we're drawing circles, the electrons are also moving in the circle. Okay. Now, 2 helium electrons are sometimes shown as a pair over here, sometimes 2 electrons on the opposite sides. Either form is acceptable. But if you're supposed to come with a higher number of electrons, like we have 8 electrons in the second shell, we always ask the students to draw them in pair. A pair on top, a pair at bottom, a pair at right, and a pair at left. I would never recommend a student to count the electrons like this: 1, 2, 3, 4, 5, 6, 7, 8. There you go. We're done with all 8 electrons. That's not how you're supposed to do it in exams. All right. Make sure you draw it neatly and you put the pairs top, bottom, right, left, and you're going in a similar way. Even if it has less electrons, take a look. Fluorine has 7 electrons in its second shell. So a pair on top, a pair at bottom, a pair at right, but only a single electron at left. So oxygen has 6. So we're going in a similar way. Make sure you properly do it and you don't change it or draw it in a messy way. For example, if we move to the 4th period, we have potassium as an example. Now, if I ask you to work out the electronic configuration from this diagram, how would you write the electronic configuration of potassium? Write, not draw.
2881.
2881. So it's pretty simple, right? So from the configuration, you can go for the drawing, or from the drawing, you can come back to writing the configuration. It should be pretty simple. Here you understand one more thing, that the first shell is completely filled. The second one is also completely filled. The third shell may contain more electrons than 8, but it is at least stable enough so that we can start filling the 4th one. So potassium is 2881. Calcium, however, is 2882, which gives you the idea how the electronic configuration works. Let me tell you that the electronic configuration in the IGCSE syllabus is only for the first 20 elements, and this is the 20th one. So this is the maximum number of electronic configuration or electrons that you're supposed to work with in this course, which I think is pretty simple. Do you agree with me?
Yeah.
Okay, good. So usually there is a 1-mark question in every paper about the electronic configuration. Now let's come to something that I was talking to you about previously. How does the electronic configuration and the periodic table match with one another. Now, the electronic configuration and the periodic table actually literally match with one another. Let's start with the group number. You would notice in group number 1, every element has the last number 1, which means their outermost shell or their valence shell has the same number in electronic configuration as their group number. So it should be pretty easy. So group 1, group 2, group 3, group 4, 5, 6, 7 work in the similar way. However, there is an exception in group 8, and that is helium. You won't see number 8 at the end of helium, because of which we had to rename it as group 0. Make sense?
Yeah.
Because all of them have 8 electrons in their outermost shell except one element, which is helium. So it gives you the idea how it works this way. Now, these are just first 20 elements. Let me tell you, no matter how down you go in a group, this rule remains the same. So after potassium, we have rubidium, which is not given over here, but the last number is still 1. Then we have cesium, again, the last number is still 1. Then we have francium, again, the last number is still 1. So this rule remains intact even you go all the way to the bottom of the periodic table. Understandable?
Yeah.
Okay, not just that. Now, they are just talking about group number over here. Let me at the same time talk to you about period numbers. Period numbers are usually written on the left. This is period number 1, this is period number 2, this is period number 3, this is period number 4, so on and so forth. Now, this number does not matches to the numbers written over here. But if you count the numbers, you'll find the same thing. For example, it's period number 4. Now, these must have 4 numbers all the way in this period. Period number 3 has 3 numbers in their electronic configuration. Period number 2 has 2 numbers in their electronic configuration, no matter how far on the left or on the right the element exists in the same period. Get the point? So
Yeah.
if we are talking about potassium and the electronic configuration is 2881, this last number would tell you the group number, right? And there are 4 numbers over here, so they tell you that it's present in 4th period. But that's not all how electronic configuration and periodic table are related. Let me give you one quick tip. If you add these numbers, 2 plus 8 plus 8 plus 1, which is equal to 19, which is actually the proton number Z of K, potassium. So these are 3 things that you need to remember about the whole electronic configuration and periodic table. First, the last number of the electronic configuration is the group number. Secondly, the total numbers which are listed in the electronic configuration is the period number. If you add all the numbers in the electronic configuration, it would give you the atomic number or the proton number of the element. These 3 points can correlate to one another, and we can answer many questions in exams. If you go through the past papers, you would see that these pieces of information have been manipulated to form very different questions in different past papers. Right?
Yeah.
Let's move on. So the period number gives the number of occupied shells or the highest occupied shell as well. So the same thing is explained over here. As I have already explained it, so let's move to the next page. Now, elements in the same group in the periodic table have similar chemical properties. Let's take an example. For example, for group 1, they all react vigorously with water. They all form the compounds with the same formula. Take a look. LiOH, NaOH, KOH, which means everyone has similar number of oxygen and hydrogen atoms. I'm literally replacing the symbols from the first group. Lithium with sodium, sodium with potassium, and there we go. We have the formula for the next element on the list. For example, all the elements in group 7 react with hydrogen to form the similar formulae acids, which is, or gases, hydrogen fluoride, hydrogen chloride, hydrogen bromide. And you would see that they have not just the same formula, they almost have the same name. So the next one on the list is iodine. If hydrogen reacts with it, what should be the formula for it? Following the
If
same
what
list,
reacts, if what reacts with hydrogen,
ID with the symbol I.
so
It reacts
hydrogen,
with continue.
yes, hydrogen iodide.
Hydrogen iodide. And what about the formula?
Will it just be HI?
Right. So it's pretty easy. It's HI and the name remains the same, hydrogen iodide. Instead of iodine, it's just iodide, as the names are ending over here. So it's pretty simple. If you see the same things, you can always come up with names for something that you're not aware of, or for the elements that even surpass the first 20 in the periodic table. All right. So all the elements in group 2 form chlorides with a similar formula. For example, MgCl2, CaCl2. What if I tell you the next element in group 2 is Sr, strontium? So what should be the formula for its chloride?
Wait, sorry, what was that?
The next element in group 2, the first element in group 2 is actually Be, then comes Mg, then comes Ca. So Be forms BeCl2, Mg forms MgCl2, Ca forms CaCl2. So Sr would form.
SrCl2.
And the next one on the list is Ba, barium. It would form
BsCl2.
Right. So it's pretty easy for us. If in exams the question comes, they give you a list of either the names or the formulae, and they ask you to predict the next one on the list. You can either predict the name or you can either predict the formula, as they have the similar chemical properties in groups. So along the groups, the working is pretty easy. The names are similar, the formula is similar, and it's easier for the student to go with a little bit of common sense and answer the question to predict it correctly. Okay. So coming next, the noble gases. The group 0 elements are known as noble gases. Why? Because they're almost completely unreactive. In fact, two at the top of the group, helium and neon, don't react with anything. We call them noble. The word noble in the periodic table means unreactive. We are also going to use the word inert in this book for the same reason. So whether I use the word noble, whether I use the word unreactive, or whether I use the word inert, it means the same thing. The lack of reactivity of the elements in group 0 is associated with their electronic configuration. Their outer shell is almost full. There is no tendency to either lose electrons, gain electrons, or share electrons for a new chemical reaction. That's why they usually do not form compounds and exist in the form of single atoms in nature. Right?
Yeah.
Okay, there is a key point over here which we need to go through. The reason the noble gases group is usually known as group 0 and not group 8, because almost all the elements in the group have 8 electrons in their outermost shell, except helium, which is an exception. We studied that exception before. Apart from that, they don't have any combining capacity. They don't lose electrons, they don't share electrons, they don't gain electrons. They have zero combining power with any other element. We call them noble for this reason. They won't be going for any chemical reactions because their outer shells are almost full or already stable to begin with. So they don't react. All right.
Yeah.
In reality, the outer shells of argon, krypton, xenon, and radon are not full, but actually they're stable enough not to react. Okay, which I've already explained. The next category in the list, after working with groups in periods and electronic configuration, is metals and nonmetals. Now, the entire left-hand side of the periodic table are metals, and a small portion on the right-hand side is nonmetals. Although the division into metals and nonmetals, it is not clear in the picture that we begin with, but there is a lot of uncertainty in the dividing line. For example, arsenic has both the properties of metals and nonmetals. So what we do is that we go for a staircase. Now this time I'm going to go explain the periodic table a little differently than I did on the very first page of this chapter. Take a look. The entire periodic table has been given just two colors, blue and yellow. The yellows are the nonmetals, which for you see a very small part in the periodic table. And you would see that the most of the periodic table is colored blue. All right. So you would hardly see 25% of the periodic table colored as yellow, and the rest 75%, third-fourth part of it, are all metals in colored blue. What we tell our students that even if you don't get a colored periodic table in your paper, you only get a simple periodic table in the paper, how are you going to work it? This bifurcation line is more like a staircase. Start from this corner and draw a staircase for yourself. All right. And when you're done with this staircase, everything on the left can be considered as a metal. Everything on the right can be considered as a non-metal. However, there are some for which we call them metalloids, something that has the capacity to show the properties of both metals and non-metals. Some properties of metals, some properties of non-metals. We call them metalloids. This one is a metalloid, this one is a metalloid, both this one and, sorry, my bad, not this one and this one is a metalloid. Most of the time,
so the ones on the edges.
So the ones at the top or the bottom of the staircase are metalloids. Yeah. But let me tell you, the first staircase is not included. Aluminum is not a metalloid. Boron is still a discussable element for a metalloid. Many scientists agree with that, many don't. So it's really a discussion. But at your level, everything on the top and bottom of the staircase, exactly on the edges, as you said, are considered as metalloids, except the first one. All right. So anything else on the right, non-metals, anything else on the left, metals. Hydrogen is also non-metal as per its origin. So it's pretty easy to work like that. Okay. You may have noticed by now that hydrogen does not really fit into the periodic table properly, although it has one electron in its outer shell, but it can't be a part of group 1 because it does not have similar properties to group 1. Group 1 is all metals. This is a non-metal. So it does not have the chemical properties of or physical properties of a metal. It has all the chemical and physical properties of a non-metal. So we call it a unique element. All right. So, but still, it can show some properties which can be related somehow to metals. That's why we still call it unique. We'll come to that a little later. Now, I've been using the word metals, non-metals again and again, but how do we define them? This is something which is difficult. Instead of defining metals or non-metals directly, what we do is that we compare their properties. So, to begin with, metals conduct electricity, non-metals don't. However, as soon as I'm going to go with these properties, I am always and almost always going to come up with an exception. The periodic table is full of varieties, though we give you a generic set of trend or how the metals and non-metals behave, but there would always be exceptions. For example, I started off with conductance of electricity. Non-metals do not generally conduct electricity, but actually one of them does, and that is graphite in the form of carbon. Silicon is another example, but silicon is more like a metalloid, and it actually does not conduct electricity completely. However, we use it for semiconductors, which conduct electricity on increasing the temperature. That's why silicon is quoted over here. Why do metals conduct electricity? Because they have free to move electrons, which we're going to explain later. Non-metals do not conduct electricity because they don't have any free to move electrons. However, carbon in the form of graphite would have free moving electrons. That's why even being a non-metal will be able to conduct electricity fairly. Moving on, metals generally form basic oxides. This we're going to study later. So I usually keep both of these points, that metal form basic oxides, non-metal forms acidic oxides, for the later parts. All right. I usually keep this for the organic portion as written over here, chapter number 17 in specific, acids and bases. Okay, so I'm going to keep this point for later chapter, both of these actually. All right. Okay, so I'm not also going to not discuss these key points as they're related. Don't worry, I'll explain them as soon as we get to chapter 17. Okay, so as a whole, if I talk about metals, metals are solids. They mostly have high melting and boiling points, high densities, but the exceptions are, for example, mercury is a liquid. That's the only metal which is a liquid at room temperature, this one, right? Metals are shiny, they have a luster, they have a shine whenever they are polished or freshly cut. Metals are malleable, they can be hammered into shape, literally by an impact force. I hope you understand what hammering is. Let me tell you, metals are so much malleable that if I take a pure gold piece, almost the size of a matchbox. Have you seen a matchbox?
Yeah.
How small it is? And if
Yeah.
I manually hammer it, I don't take help from any machine in the world. I just do it with my own hands. In a few days, after continuous hammering, I can change that small matchbox sized piece of gold into a sheet which can cover the largest football stadium on the planet by manually doing it. If I take help from machines, I can easily cover it enough to cover 4 largest football stadiums of the world, maybe even more. That's how much malleable they are. We're talking about hammering into shapes. Most of the time, they're sheets. That's why I given an example of a sheet. Next property is ductility. We can draw them. Draw means pull them, stretch them into wires. Stretch them from both corners, you can convert them into wires. They're very good conductors of heat and electricity. They can easily form ionic compounds when they react with halogens. We're going to discuss that later. Positive ions, discuss that later. Instead of going with the positive ions part, I tend to tell my students this point in a different form. Metals like to lose electrons. This is something you might want to remember for upcoming chapters, especially the morning chapters. Non-metals, on the other hand, would have an entirely different set of properties. To be exact, opposite set of properties. If metals were mostly solids, non-metals are going to be mostly solids and gases. Some of them are solids, most of them are gases. If metals had high melting and boiling points, non-metals have low melting and boiling points. If metals had high densities, most non-metals have low densities. There was only one liquid metal on the list. There is only one liquid non-metal on the entire periodic table, and that is bromine. To this low melting and boiling point, the exceptions are carbon and silicon that we're going to discuss later too. Metals were shiny. Non-metals are usually dull. Although they come in a lot of colors, but they're usually dull. Metals are malleable, can be drawn into shapes, or ductile, can be drawn into wires. Non-metals tend to be brittle. When I use the word brittle, it means you can't shape it. If you try to shape it, if you try to use a force, if you try to push it, it would break instead of getting into shape. That's what brittle means. Clear enough? Moving on, they have the same type of, they don't have the same type of shine as metals. They don't conduct electricity except graphite. They're poor conductors of heat except diamond. And they tend to gain electrons. Instead of going with the negative ions part, I ask my students to note and remember that non-metals like to gain electrons. So it's pretty easy for students to bifurcate them or how they're going to behave in bonding. Most of the time, metals would like to lose electrons. Most of the time, not all of the time, most of the time, non-metals would like to gain electrons. However, non-metals sometimes are also capable of sharing electrons. which actually completes this chapter for us.